Good evening, Year 11s. Welcome to the first installment of Toby Teaches Chemistry. So I'm doing season 2. This is our season 2. I have already completed the top 5 worst questions answered on your mock paper, and I'm now at the request of many Year 11s, I'm going to be doing 5 topics which people have asked me to cover. So I'm going to be doing in this series, I'm going to be working through, let me just quickly check. So in episode 1, which is today's, I'm going to be running metal extraction, followed by industrial chemistry, organics, periodic table, and energetics. So 5 more episodes. And again, I'm going to try and be as quick as possible. Going to do a crash course, try and get it all done in an hour. And I'm going to run through the preliminary work that you guys should have done in advance of this program. And then you guys can have a look at the follow-up work as well. Okay, so let's share my screen. Share. Right, okay. Just going to quickly, usual thing, folks. So these are my learning objectives for today's lesson. So I'm going to be able to use the reactivity series. You'll understand the word use in this particular setting. Then I'm going to be following it up with key extraction methods and going through carbon reduction for iron, electrolysis for aluminium, and I will then do other metals as well. And that'll be really important for me to focus on exam questions. And I'll throw out some questions during the webinar. And then I also want to cover the understanding of key terms, reducing agent being a key one. Okay, so I did the same thing that I've done in the last webinar, which was I wanted to show you where in your specification this lesson comes. And the answer is it comes in a lot. So we've got 4 key areas where this makes an appearance. The first one is describing the formation of carbon dioxide through the thermal decomposition of metal carbonates. And they specifically give an example of copper 2 carbonate. Shouldn't really be highlighting that in green. What I should be doing is highlighting that in blue-green. Always nice to be able to attach our colors. There's our blue-green or turquoise. That really wasn't the color I was going for. Let's try that again. Let's go for that one. Oh, it's wanting me to select it. There you go. Let's see if that works. So we've got copper carbonate, which starts off at a blue-green. Then we're going to drop into the reactivity in order of metals, conditions required for rusting, and then onto our preventing rusting. So barriers, painting, oil, galvanizing, sacrificial protection, zinc in particular, and magnesium. Understanding the terms oxidation, reduction, redox, oxidizing agent, reducing agent, in terms of oxygen and electrons. And then it drops into the main key area of your specification. And please note, any students here that are doing dual science, the extraction of metals section is predominantly for triple only. However, all of these key bits at the beginning that I'm going to do at the start of my webinar are ones that will also be on your paper as well. So hence paper 1. So definitely worthwhile. Definitely worthwhile sticking around at least for the first bit. I will mention the crossover when it happens. Okay. So I think the first thing really for me to talk about is I'm gonna be focusing predominantly on metal extraction. And even though that this is triple mainly, I will make a drop in for all those dual sciences. But can I also say that this is great chemistry, and it's really, really good even if you're a dual scientist to follow it anyway, just because it means that you'll be able to access questions at a higher level and make the rest of your papers look a little bit easier. So, okay, now the first thing we need to talk about, guys, is metal ores. Now, metal ores actually gains a definition at this point. So our definition is a rock. And in fact, I'm going to bullet point this and show you where the marks come from. I do want to also make a reference to the fact that a lot of the time now they're making definitions down to 1 or 2 marks, even though you need multiple points that are beyond 2, maybe 3 or 4. So metal ores, we have got a rock because that's where metals come from. We dig them up out the ground from mines. A rock that contains sufficient, I don't like that word, let's simplify it, enough metal or metal compounds, third bullet point, to make it worthwhile extracting. 3 bullet points for that definition. So just to be clear, this is all about making money. Yeah, everything in chemistry, everything in industry is about money. And we would definitely not extract metal from a rock if we can't make money off it. It's nice just to talk about a couple of examples of ores and not ores. So if we talk about, a great one is sandstone. So sandstone is orangey red in color. Now, sandstone is actually white if you actually get pure sandstone, but its impurity, notice the key word, its impurity is iron oxide. Now, please note the formula, and I need to be really careful here because you guys get asked this a lot. This is iron 3 Roman numeral oxide. Iron 3 oxide, I don't like the first bracket, there we go. So iron 3 oxide is rust, and it's red, and this contaminates most rocks in reality. So is sandstone strong? No, it's a sedimentary rock, so it's relatively soft in relation to rocks as they go, Lucas. Good question. So rust is red, we all know this, and in small portions, it'll make something appear orange or pink, which is what sandstone gets. Now, there isn't enough. Sandstone does not classify, it is not capital letters, an ore. Now, the reason why it's not an ore is because there is not enough compound, not enough metal compound to make it worthwhile. We could get metal out of it. I could extract iron out of it. By the time I've paid for the process, I'm going to get such a small quantity of metal that I'm not actually going to make money. So it doesn't qualify. Now, at this point, I need to now mention your main metal ores. And you guys need these, folks. They do like to name them in your exams. Key ores. First one is hematite. So hematite is our main ore. This gets mentioned more than any other. And of course, this is iron ore. And its formula is Fe2O3. There is another one called magnetite. Now, magnetite, and its name actually tells you a property about it, it's actually magnetic. And it's also an iron ore. But in this case, it's FeO. And it's nice to talk about the difference, because magnetite, of course, is rust. This is iron 3 oxide. And magnetite is iron 2 oxide. Far rarer in nature. Iron 3 is the common one. Now, this has come up a couple of times over the last 10 years, and it comes up mainly in terms of percentage composition. This is one of our calculations that we picked up, and the reason why it's nice to run this one is to explain which metal ore is actually worth more money. So if you want to work out the percentage of iron in Fe2O3, so Fe2O3, I have 56 times by 2 over 56 times 2 plus 16 times 3. And then I times that whole number by 100. Now, I seem to recall, by the way, I'm pulling numbers out of my head here because I haven't actually got a calculator on me. I seem to recall that spits out around about 70%, which is a reasonable output for an ore. If I now look at the percentage of ore in magnetite, which is FeO, I've got 56 over 56 plus 16. And I seem to recall that spits out around about 78%. Magnetite is far more valuable than hematite, but much rarer. Lots of people who end up finding magnetite on their land will often have their land purchased by iron extraction companies because it's worth a huge amount of money. Because when you start doing this on a ton basis, you end up making an awful lot more money just sheerly because you get 8% more metal. it's nice for me to run the percentage of elements in compounds. It's a lovely calculation, and it's a really nice setting for that to make an appearance for. Okay, other ores that you guys pick up. Other ones of super importance. Malachite. So most people will recognize this from my lesson, partly because I pronounce it slightly differently. And malachite is a copper ore, and it is copper carbonate is the chemical compound. Now, that one we're going to talk through quite a lot, because copper, of course, is actually is becoming rarer and rarer. It's a finite resource. Metals will run out, by the way, folks, and copper's on the list of one of the first ones to go extinct. We are using copper at a huge rate. We use it for so many things, including pipes and coins. We use an awful lot of it. Right on both times for the percentages. Oh, Lucas, thank you so much, Lucas. Lucas, you've just earned yourself some commendations for running my maths for me. Good man. God, do you know what? I'm super impressed with me remembering my percentages there. That's a little bit ridiculous, to be fair. Commendations. Comms. Lucas. Great job, Lucas. Thanks very much. Times one. Great job. Really appreciate that. So all I actually remember is the fact that the magnetite is give or take around about 8 to 10% more, and the other one was about 70. So it was just a bit of luck, to be fair. Okay, so copper carbonate. Copper carbonate is a super important chemical to come across. This is, of course, a beautiful stone when we see it. And at this point, I'm going to drop over to my internet and quickly Google copper carbonate, because it's a lovely stone. If you click images, they're going to give me the powdered form of it, of course. And if I'm looking for the rock, there's the rock. It's a beautiful, beautiful rock. Beautiful green color. And it's primarily made of copper carbonate. And that is, by the way, for your studies, and you need to know this, folks, it is a blue-green compound. Oh, I don't like how I've just done that. If I make that fatter, it'll make it a whole... That still really hasn't helped me. So copper carbonate is blue-green. Other ores that are good to talk about. Now, you don't need... Looks like jade. Not dark enough for jade, I don't think, Amira. But yes, very similar. It's actually... Jade has an almost translucent appearance to it. It's almost see-through. Whereas... malachite is very much opaque. It's not see-through at all. Other ores of interest. Now, at this point, those are the only two ores that you're expected to name, which is hematite and malachite. Other ones include rutile. Rutile is a lovely one. That's titanium, TiO2. Other ones include wolframite. And all of these I'm going to make an appearance in my webinar today. That's WO3. Lovely this. If I now translate this into real chemistry speak, this is titanium, and it now gains... Oh, year 11, first question. What Roman numeral goes in that bracket, please? And second question, same thing for tungsten. This is tungsten. What Roman numeral goes in those two brackets? 3 accommodations up for grabs. Huishan, you're wrong. Right, Huishan has gone and said 2, and she said 2 because of that 2. That is not that. Donna's said 111. Lucas has said 18. Right, oh dear, that's a disaster. Okay, so no, yes, quite, no is right. So let me just quickly explain. Oh, Amira, great job, Amira. 4 is correct. Outstanding, young lady. So titanium 4 oxide. Let's explain why. Because I've got Ti bonded to 2 oxygens. Now, those oxygens are O2 minus. We always know what oxygen is. Now, for titanium dioxide to have a 0 charge, titanium must be cancelling out the total, so it must be in a +4. Lucas, 4 and 6. Well done, Lucas. 6 is correct. Well done. For the second one, nice to see how this one does it. Same thing. Tungsten, question mark, O2 minus, O2 minus, O2 minus. We need to get to 0. We've got 6 minuses to cancel. I need 6 plus. So we've got 6 plus there on tungsten. Cool. Well done, guys. Really impressed. So I've got Amira, who's just picked up 1, and Lucas, who's just picked up 1. Well done, Lucas. You're now on 2. And Amira's just picked up 1. That's excellent. Love it. Times 1. Cool. So these, by the way, year 11, these charges on metals are really important. They come up a lot. Can I just now quickly make a nice little addition to your knowledge? These Roman numerals, they go from 1 to 7. That's all you need to go up to. The reason being is because you're never going to find a metal that's in a higher charge state than +7. So that's as high as it goes, folks. That's all you have to remember. So 18 was definitely not good. Dana, 111. That is definitely not the right answer. I thought that was very entertaining. Just since that Dana's kicking herself over her crazy 111, I'm going to give you a couple of others. Here is, I'm going to go for tin S. I'm going to go, I'm tempted to really make you guys struggle on this one. I'm going to go for a 4. What's the charge on the tin, please? What's its charge? Sn plus what? I'm going to give you one more. Let's go for antinomy. Antinomy is, I have no idea. I really should know what the formula is, what the element symbol is for antinomy, but I don't. It is SB. Let's go for SB. I'm going to really push you guys now. I'm lagging. Yeah, sorry, yo. Sorry. SB. Let's go for something horrible. Let's go for S2. What's going to be the charge on, and that's going to really make you guys struggle because you're going to have to use the periodic table. The winner was Lucas again at +4, closely followed by Johan. Ke, I like it. Donna has no idea what's going on. I've chopped in it. You see, the problem is I swap in you guys for a different element and you panic, and you should never. Everything comes from my beautiful, wonderful, gorgeous periodic table. So what's going to be the charge on antinomy? I'm wondering whether Lucas and Daniel have already got there. Lucas scores again. Well done. And it's absolutely right. So it's nice to look up how we're doing it. SN question mark. But this time we have 2 of them. So we have to be aware of that. We have got O2 minus, O2 minus, O2 minus, and O2 minus. Total minus is 8. So I need 8 pluses. And now I've got 2 of them. So that must be in a +4. So tin was in a +4. And antinomy, same thing again. I've got SB. I've got 1 of this time, but now I've got S. And S is in the same group. It's nice for me to be able to actually write on this. Really hoping this is going to do what I wanted to. There we go. And S is in the same group as oxygen, so which means it's also an S2 minus. So I've got S2 minus and S2 minus. Total 4 minus. So therefore, to get to 0, which is what this is, it must be in a +4 as well. Well done. Lucas scoring all over the place. Well done. Really impressed, Lucas. You're doing great chemistry. Right. Okay. So now we get, at this point, I'm now going to chop, now that we've just quickly had a quick chat about ores, it would be nice now to talk about our means of extraction. So just quickly going back to my learning objectives, it's nice to do my 3-part plenary here, is what our teachers often says. Know that most metals are extracted from ores found in the Earth's crust, and unreactive metals are often found uncombined. Okay, just quickly need to cover that uncombined bit. So guys, lots of metals which are incredibly unreactive, like gold and platinum, are found what's called native. So silver, gold, platinum, these are incredibly inert metals, and these tend to be found native. They just tend to be found as their metals themselves. They're not combined to oxygen. They haven't picked it up in that time. So these guys tend, mercury is another one that can be found native. Rhodium, lots of precious metals tend to be found native. Okay, so I get to take the top one off. The next one, explain how the methods of extraction relate to its position in the reactivity series. Okay, so at this point, I'm just going to quickly move their commendations out of the way. So, okay, the reactivity series is a beautiful thing, and you need to know very little about it. You don't need to know it all. Now, people often say, do I have to learn it? You don't. You just have to remember key people. The section that I remember is aluminium down to iron. Those are really the only ones I tend to remember. Al, C, Z, and Fe. The reason being is carbon is super important because, of course, everybody above carbon, all of these guys are extracted via electrolysis. And the reason being is because they are more reactive than carbon. More reactive. And notice the comparison than carbon. I'll come back to that in a minute. Anybody below carbon, I'm going to try and clean that up and make it a bit better. Anybody below carbon is extracted via carbon reduction, which is the blast furnace. Blast furnace, otherwise known as carbon reduction. So this isn't complicated. And in fact, what I'm actually going to do is, rather than doing the electrolysis bit, which I covered, please stop calling me, Daniel's giving me an actual, please stop calling me a cute zebra. Seriously, please stop calling me a careless zebra. Instead, try learning how copper sucks gold. That's really funny. Sure, that's really great. I don't even know that. I don't even bother. I just know the fact that I know the key important people, and that's all I need. Okay, now just to quickly mention hydrogen. Now, hydrogen is important because it comes in place in terms of our acids. We know that acids provide me with H+, and any metal below hydrogen won't react with acids. And it's nice for me to talk about this reactivity series. And also, just to also tell you what it's really about. It's to do with the ability, metals like to lose electrons. The higher up you are, the more you like to lose electrons. The lower down you are, the less you like to lose electrons. So if you're above somebody else, you can take them from it. That's what it's all, this is what it's all talking about. So if I have, I'm tempted to use an example. So I'm going to pull two people out. Let's pull zinc and iron. So if I take zinc, we know is higher in reactivity compared to iron. What that means is zinc likes to lose electrons more. It wants to lose them. What that means is that if I add iron plus to this, because zinc is more reactive than iron, it's going to swap. The zinc is going to give its two electrons to the iron. And it's all to do with this idea. I mean, don't get me wrong. To look at it in terms of electrons can get a bit confusing, and you don't need to. All you need to remember is that the more reactive one will give the other person electrons or steal oxygen. That's nice to remember, oxidation. And I'm going to do that right now. So the next bit for me to talk about before I'm leaving ores, and I'm dropping now into oxidation and reduction. Oxidation and reduction. Now, you learned, guys, is that like displacement? Yes, it is just like displacement. Does like Fe have less shells or something? Lucas, it does come down to the atomic structure, but you don't need to know actually how it comes about. So the key things to oxidation and reduction, folks. Number one, oxidation. Oxidation is, I'm going to have a double dot, is gaining oxygen. That's important. That was the first thing you learned. And I really want to emphasize this, folks. That is the very first thing you learned when you came across that word. If somebody gains oxygen, somebody gains it, then they're going through oxidation. Let's look at an example. Rusting. Iron plus oxygen goes to Fe2O3. This here, let's balance the equation, common denominator 4. So we've got that is oxidation. It is absolutely true. Iron has gained oxygen. That is oxidation. Next thing, reduction. We then learn reduction is removing oxygen. This is still important. It still plays a key role, and it actually makes questions easier at times. Let's show an example. If I have Fe2O3 and I add, let's add somebody more reactive. Let's add aluminium. And I'm going to form aluminium oxide and iron. Now, guys, I really need to stress this. I'm going to balance that. 2 of those and 2 of those. Right. This reaction is important, folks. And this is classed as a redox. This is redox because it's both. I have that guy losing, so this guy's going through reduction. I do that as red. And then this guy is gaining. That guy's gaining, so that's ox. So we've got, this is both. However, when it comes to metals, we tend to talk about the extraction of a metal, and if they were focusing on iron, we would call this a reduction. Whenever we're talking about if we want a metal, we don't tend to refer to it as a redox. We tend to refer to it as a reduction. And I know that that's difficult because people go, but hang on a minute, it's both. And I get that. When it comes to a metal, we tend to talk about it in terms of reduction. I'll show you some questions near the end. Now, this equation, folks, is actually quite important because this reaction, which I'm going to do in red, is called the thermite. And this makes an appearance, a good 2 out of 3 papers, thermite will make an appearance. The reason why it makes an appearance is because it's a rather special reaction. It is incredibly exothermic, which means it gives out a vast amount of heat. And in fact, so much heat, give or take about 2,400 Celsius, and it produces liquid iron. You guys will have seen this on YouTube, and if you haven't, please Google it or YouTube it. They're brilliant videos. They're really, really great. If the redox reaction doesn't involve oxygen, could you refer to loss or gain of electrons? Of course you can. Yes, you can, Ekin. Of course you can. Spot on. So this reaction is really, really special. It's actually used. That's how they make breach charges. Oh, I didn't know that. I know that they use this to weld railway tracks, and that's actually most of the time where it makes an appearance. If I quickly Google thermite GCSE question and click images, that's usually not a great search, to be fair, but it would be nice to actually, they often have a diagram of the thermite on a railway track. I can attempt to draw it, but I can attempt to draw it. Oh, it was not there. A bit sad. I thought it might be there. But they tend to have an image of this, which is, they have, I'm going to do that in black. So they have a railway track, and above it, here's my railway track. And what they have above it is this rather bizarre looking contraption, which looks like a vase on top of it. Views going inside. And then this goes onto a box like that. That was a terrible, I'm going to fix the box. There you go, railway track. And what happens is we've got a mixture of iron oxide and aluminium powder. And what this is, once it's lit, it produces such hot through the bottom here, pours molten liquid iron, and then it fills the gap. The reason why it's used to fill the gap is because railway tracks are such thick steel that trying to actually weld these together is impossible. You'll only weld the outside. So what they do is they pour in a liquid metal into the gap, which is molten iron from thermite. And it goes into the gap and then sets. It's a rather lovely use of a chemical reaction. It's a brilliant reaction. If anybody wants me to do that in school, I'll do a really big demo of that. We'll probably have to go outside. I'll do like a flower pot size production. It's amazing reaction. It's like a proper firework. It's great. Happy to do that. Okay, so it's nice to talk about oxidation reduction in terms of oxygen. Then we do get to come across it in terms of electrons. I am just going to quickly throw in oil rig. Oil rig, oxidation is the loss of electrons. That's important. And reduction is gain. So it's nice to talk about it in terms of electrons and in terms of oxygen. You should know both. It's really, really useful. You come across it an awful lot. Okay, so at this point, I'm going to go into the actual extraction processes that we use. And it talks about how the extraction methods used for key metals, including iron and the electrolysis of aluminium. I'm going to actually do 4 metals in reality. And the reason being is, even though it's not on your list to know, they ask it and they love doing this. Okay, so the first thing is we need to talk about iron extraction. So iron extraction requires me to have a diagram. I'm going to attempt to draw it. I could cut and paste it, but I actually quite like drawing it. It helps me remember. This is called the blast furnace. It's a lovely name. It was named because of an actual particular part of its structure. So we have a huge container, huge, these things are 4 or 5 stories high, a huge container, which looks like this. Now, lining the inside, I'm going to have, there's a pipe going in here, pipe there, then it comes down level. And then after that, we get 2 more levels, which I'm going to go out there and there. So this is what it actually looks like. Now, here's what they do in this structure. So the first thing is, we have got these here at the top are air inlets. This here, they pump in air. Now, this is to provide air in. It's nice meeting you the other way around. In air in. I prefer air in. I'm going to fix that. So the air goes in at this point. And that really is, of course, everyone knows for oxygen, but we don't need to put in pure oxygen. We can just do this in terms of air. The next, also just to point out that this has like a funny kind of funnel there at the bottom of it. Now they fill the blast furnace with 3 materials. The first one is we need our source of iron. This is hematite. So this is our iron source. Next, this is our rust. Then we need a reducing agent, and that is coke. Now I'll explain that is called reducing agent. The agent is who is stealing oxygen. Now the third, and I'm going to do this in a different color. I'm going to do this in green. The third person going in is limestone. Now limestone is there to remove impurities, and actually one in particular. So this removes silicon dioxide impurities. I'll show you all the equations for this in a minute. So the limestone there's just for removing impurities, but the other 2 have got more important things going on. So just to now tell you, they add loads and loads and loads of coke, which of course is carbon, and they put about, give or take, it's about a 5-to-1 is what they do. It's about a 5-to-1 ratio of these 2. So if I was to draw carbon or, by the way, coke is purified coal. So if I was to draw these, I've no idea how many I've done there. 4, 5, 10, 16 I've put in there. And then, so if I do 16, let's do 20, 16, 17, 18, 19, 20, and it's about 20. And then for every of those, I'm now only going to include rust, of course, is browny red. So I'm going to go 1, 2, 3, 4, 5. We've got loads and loads of carbon and a very small amount of iron oxide. So what's now going to happen in the process? Now, this is what makes things tricky, because in order to extract metals, and this is, by the way, a really important thing, all metal extraction requires high temperatures. All metal extraction needs high temps. This is just a fact. Now, that high temperature usually comes from burning fossil fuels. However, in this case, they can get it from the blast furnace itself. Because what they now do is set fire to it. And the coke, which is carbon, so this is now the heat source. And what happens, you set fire to it and the carbon burns to form carbon dioxide, which goes into the atmosphere. And that produces heat because it's exothermic. But then some of it doesn't escape. And the carbon dioxide reacts with more carbon to make 2 carbon monoxides. And that produces heat as well. So these are the 2 equations for the heat in the blast furnace. That's where 1000, by the way, the first reaction produces about 900 Celsius, but the second reaction pushes it up to 1600. So these are our 2 equations for the heat of the blast furnace. Now there's an extra kicker, which is rather lovely, which is this guy. I'm going to do that in there. So carbon monoxide is rather nice here because this is also our reducing agent. This is what is going to steal oxygen for us. We now have iron oxide. Hematite is going to react with carbon monoxide to form carbon dioxide and iron. Now, people are often saying, oh, can it not just be iron oxide reacting with carbon? Yes, it can be, but that's actually very rare. The reason being is carbon's a solid, and the chances of 2 solids coming together would only be at the surface, whereas carbon monoxide is a gas. So it's going to bump around, it's going to collide with stuff, it's a far better. This happens 95% of the time, and this happens 5% of the time. However, both equations are correct for the formation of iron, and the iron comes out liquid. My diagram, which I now need to highlight these 2 exit points. Now, the liquid iron is heavy, and it drops out the bottom. We produce molten iron metal. Now, that iron is tainted. Mexobendo, breaking bonds, etc. So why does that create CO2? Why is it exothermic? Good question. Okay, so Johan, that's actually a very difficult question. What you need to do is look at the energy required to break this. So, okay, this is Johan's fault. Don't blame me. This is the energetics. I'm going to do a webinar on this, guys. So don't worry. So we need to look at taking carbon as a solid and smashing it into carbon gas. That's going to be endothermic. It's going to cost me, let's say how much it costs me. Let's say it costs me 200 kilojoules per mole. Next, I can then say, right, I also need to take oxygen and I need to smash it into oxygen atoms. So that's also going to cost me energy. It's also endothermic. Let's say that costs me, I can actually tell you that's 495 kilojoules per mole. And then I tell you that the bonds being made are 2 carbon-carbon double bonds, and each one of these bonds is 690, something like that. I don't know, it's maybe not quite that high, but times by 2, so I'm now going to produce something like 1400 kilojoules per mole. So I have an excess of, let's call that a nice round 700. I've just produced an excess of 700 kilojoules per mole. It's all about looking at the bonds. You've got to calculate it all up, Johan. You've got to look at all the numbers. It can be done. It is part of your GCSE. I will do energetics at a later date. Don't worry, folks. So anyway, I'll get rid of all that energetics question. But I can tell you that it's actually very exothermic. All combustions are, quite a nice thing to do. Right, next. So now that we've got these are here. These are our reduction equations. Please note, they are redox, but I'm not calling them such. I'm calling them reductions because what I'm after is iron metal. So we tend to call them reductions in regards to the metal. And if they ask you why, because it has lost oxygen is why it is a reduction. Nice to go back to that very first bit. Next thing, where does the limestone come in? So limestone, I'm actually going to make my pen a little bit thicker because I definitely think it's worthwhile doing that. So where does limestone come in? So limestone, which you must know, year 11, you've got to know this stuff well. I'm trying to zoom in and my laptop's giving me trouble. So limestone is calcium carbonate. You've got to know that, folks. Right, calcium carbonate, when you heat it, it will go into calcium oxide and carbon dioxide. Carbon dioxide escapes to the atmosphere. And you guys wonder why global warming is such a bad thing, because we're producing carbon dioxide in every single thing that we do. Now we've produced calcium oxide. And calcium oxide is a base. Now that base is going to react with acidic silicon dioxide to form calcium silicate. Its common name is slag. So this is going to actually, this is a solid, and we produce liquid slag. Now that, didn't we do this last Thursday? Don't know. I didn't do it. I might have done a little bit of it. If you were to use the other iron ore with FeO, would the same blast furnace work since it has less Fe and less O2? Yes, oh my God, you'll make more, Johan, because it's 78% iron instead of 70%. Oh my goodness, it'd be happening so much quicker because it's having to do less work and produce more metal overall. How to get silicon dioxide? The silicon dioxide is sand, and sand is the most abundant compound on this entire planet. It is in every rock you find. If you pick up a stone, 40% of it at least will be sand. And so we've got to get rid of it, which is why we add limestone. Right, and just to now tell you, it's nice to come back to my original diagram. So on the bottom is liquid iron. That's because it's heavy. Floating on top of it is liquid slag, which is a black glass, which now floats out calcium silicate. It's sold now, by the way. It's used for roads. That is absolutely correct. That's what the black chips are in the road. That is what that is. It is calcium silicate, and it's used on road surfaces. We used to bury it, but now we sell it for the making of road surfaces. It's mixed with bitumen in order to create road surfaces. So it's really nice to see all of the things appearing in the blast furnace. Now, it's nice for me to just also say there are many metals that use the blast furnace. Let me give you another example. So I go back to my reactivity series. So I grabbed my reactivity series earlier, which is up here. So other metals that do it, tin and lead. Zinc also does it, and so does copper. Right, I'm going to now do copper's extraction, because copper needs talking about. Because copper is now very special. Okay, title is copper extraction. Now, copper extraction. Now, copper is found in turquoise copper carbonate. Now, this is getting rarer and rarer, folks. There's actually very little of it left. It's running out every single day. So as it's now started to run out, we've had to change our extraction method. Now, the first method is to use the blast furnace. We take copper carbonate and we heat it. It starts off blue-green. We heat it. Now, guys, every year this is on your paper. And when you heat this, it turns into copper carbonate, and the CO2 is released into the atmosphere. And copper carbonate is black. So I'm just going to try and shade that in. It turns completely black. So real change in color. Now that we've now changed it into copper oxide, we can now blast furnace it. Same picture. Air inlet, out. I'm trying to get it all in. Out, in. There we go. Air goes in at the bottom. Air, of course, is to provide the oxygen for the carbon will react with oxygen, which is coming from the air. That oxygen will turn into CO2. but then some of that CO2 won't escape and react with more carbon to turn into carbon monoxide, which is going to be our reducing agent. That is now going to react with copper. So the copper, which is the green copper carbonate, sorry, my tablet is really not behaving. It's not behaving the way it should. So the green turquoise copper carbonate, which is, I need to try and choose somewhere. No, black copper oxide, sorry. The black copper oxide is now going to react. I thought bitumen was the stuff for roads. Yes, but bitumen is it's a black liquid when it's hot. When it solidifies it would become a perfectly smooth surface. You wouldn't want to use pure bitumen because you'd have a surface which looked like a shiny plastic, which is not great. So we want to add a bit more grip to it. So we mix it with a solid that's usually just getting buried anyway. So we now react that with carbon monoxide or carbon, either one, and we make copper oxide and carbon dioxide. And the carbon dioxide is let off into the atmosphere. And I produce copper metal. And once again, the copper metal comes straight out the bottom. So this comes out as liquid copper, and out the top, of course, out that one comes slag again, because limestone is still added to get rid of the sand. They're always there. Now, at the end of this process, so there are lots of these reactions, and it works for all of them. Now, there is one problem with the blast furnace. It creates high, we have carbon impurities in our metal. Now, carbon impurities, this makes the metal very brittle. It's otherwise known as cast iron. Oh, my tablet is not behaving. No, it's really irritating me. So carbon impurities. So what actually comes out, so if I just draw the bottom of the blast furnace, and this is our pipe that has the molten iron coming out of it. The iron is actually not pure iron, but it is actually steel. It is actually high carbon steel, which is far too brittle. And by the way, just to now tell you why it's so hard, because I've got little black carbon atoms here, and they're different sizes. So carbon atoms, and we've got iron atoms, and they're different sizes. Oh, just behave, will you? It won't minimize. I'm sorry, folks. It's really, really not doing what I want it to do. There we go. So they're different sizes. So we've got different sizes, and what that means is it will disrupt the layers. Different size atoms. This will disrupt the layers. Disrupt layers. Layers can't slide. So it makes it very hard. Layers can't slide. So it makes it very, very, very tough. This is called cast iron, otherwise known as pig iron. The reason why it was pig iron is because they used to cast it into these funny little piglet-style shapes. But it's high carbon steel. It's very, very tough and very, very brittle. Not malleable at all. Way too much carbon. So now what we need to do is we need to actually purify it. We remove the carbon. What we now do is we actually have a rather cool machine called a Bessemer converter. This is removing carbon from steel. So the way we do this is on a rather cool device, and it's a rather simple one to boot. What it is it's like a funny, it's a tray like this, and that tray has holes in it. It looks like, folks, what it looks like is one of those air hockey tables. It's a rather cool device. It's an air hockey table. Now, what they do is that an alloy? Yes, it is, Amira. It is an alloy. Steel is an alloy of carbon and iron. 95% iron and 5% carbon is high carbon steel, very brittle. Now, what we do is we pour steel, high carbon steel, over this, and the liquid, which I'm going to draw in like a red color, the liquid flows down here. Now, as it flows down there, we pump oxygen gas up through the holes. And the oxygen gas, this is O2, the oxygen gas bubbles through the metal. And because carbon's more reactive, the carbon reacts with oxygen and turns into carbon dioxide, and it bubbles away into the atmosphere. So in goes a mixture of iron and carbon, and that's steel, and out comes pure iron. So we can actually adjust the amount of carbon in the iron very cleverly now. We can actually do it quite accurately. So we use this method, and it's just simply bubbling air through it, and it removes the carbon by reacting with it, and we just put the CO2 straight into the atmosphere again. Cool. It's called if anybody's interested, it's called a Bessemer converter. Cool stuff. Okay. So we've kind of covered the blast furnace. I've got one more steel to mention at this point, which is steel. You guys have 3 steels to know about. There is low carbon steel. So this is strong, but still malleable. This is what your cutlery usually is. There is high carbon steel. Now, high carbon steel has no malleability whatsoever. This is the cutlery you get from IKEA. It is complete. You can't bend that. I'll bring some into school to show you guys. High carbon steel. It's very hard. Tough. It really, really tough. Very hard. Very strong. Very strong, but also very brittle. If you hit it hard enough, it will shatter like glass. Low carbon steel is hard, but still malleable. Still malleable. Not as malleable as, say, pure iron, otherwise known as wrought iron. Still malleable. We use it for things like train wheels. Can't you sell the CO2 for fire extinguishers instead of letting it go into the air? Lucas, yes, they do. Quick question, would it be more beneficial to do a preliminary work after or before the webinar, or a bit of both? Ben, you should do the preliminary work before and then the follow-up work after. It's called preliminary for a reason. Yes, I agree. Stole my line. Brilliant. Would it be better to sell it? Yes. Oh, do you know what, Lucas? It's such a lovely idea, and we do sell some of it for carbon for fire extinguishers. But we make carbon dioxide a ton a minute. I mean, heck, if you're interested in knowing just how much we make, I'm sorry, guys, I'm off topic. I'll get back onto it ASAP, I promise. This is called worldometers. I promise I won't spend very long on this. I just want Lucas to realize, Lucas, there is no way, unless you're making where is it? Health, energy, water, food, carbon dioxide. Lucas, unless you're making 8.5 billion fire extinguishers, then you're really not, and that's in tons. You know, that we just make so much, it just becomes completely unfathomable. We really can't, just too much of it. Okay, the other steel is stainless. Stainless steel is the reason, of course, is because it doesn't rust. This does not rust. And it doesn't because we add in iron, we add in carbon, and we add in chromium. Chromium is a beautiful metal, and it stops stuff from rusting. So it's nice for us to know about that. We just mix in to change the properties. Okay, so we've covered the blast furnace. I'm going to go back to copper because copper's awkward. Copper is now running out. We needed a cheaper method, and we found one. We now take copper carbonate in what is called low-grade ore. This is ore, this is a rock, which before this method wasn't worth extracting. And it was too expensive even to use in the blast furnace. Even with carbon being as cheap as it is, this still wasn't worth it. We now have made a better method. So what we now do is we take this rock, which contains an amount of metal, let's say 10%. Not enough to make enough money in blast furnace, but it's enough for this. I'm going to dump this greenish, bluish green rock, which is a bit rubbish. I can show you pictures, by the way, of low-grade If I just quickly do malachite, I've made a right mess of that. Malachite high grade. And look what we see. We see beautiful malachite. That's high grade malachite. That is 90% plus copper carbonate. If we go malachite low grade, look at the difference. The difference is most of the rock is just dirt. This is really bad quality. This doesn't have a huge amount of green in it. It's mostly sand. So, usually not worthwhile. But we came up with a new method. You add the rock to sulfuric acid. Dilute sulfuric acid. And you now warm it. We now warm it. And the copper carbonate reacts with the sulfuric acid to form blue copper sulfate and water and CO2. How did I know the CO2? Carbonates. All carbonates make carbon dioxide. Yeah? But now I have blue copper sulfate. Now I can do a second reaction. I take the blue copper sulfate and I add scrap iron. And because scrap iron's cheap, doesn't really cost much. Costs next to nothing, really. And I now make copper metal and iron 3 sulfate. Now that is iron 3 plus, that's SO4 2 minus. So that requires 2 brackets 3. Delete my numbers. There we go. I'm going to make iron 3 sulfate. You can, by the way, they allow you at GCSE just to do that, by the way, if you want to, making iron 2 sulfate. So, kind of a neat reaction. And we now get copper metal. So it's super cheap. It requires warming, 60 degrees Celsius that requires. That's the lowest temperature we've ever come up with. And it's really cheap because we're using scrap iron, because it usually just goes into the bin anyway. So copper makes an appearance quite a lot at GCSE. Right. At this point, I'm going to talk about other metals. I'm going to talk about titanium first. So titanium comes from the rock rutile, and it contains titanium dioxide. Now, I can now tell you that titanium on the reactivity series, let's go back to my wonderful reactivity series. Gotta love my reactivity series. Let's see if I can make my tablet do what I want it to do. So titanium, my tablet is not behaving. So titanium fits in about there, Ti. So it's below carbon. What that means is we should be using blast furnace, but we don't. So now the problem is if you use carbon, you form TiC. This is titanium carbide and CO2, which is a disaster. This makes us incredibly sad. It forms a compound called titanium carbide. The next thing is now, because we can't use carbon reduction, that's out the window, we now have to switch to electrolysis. You can't use electrolysis. The reason being is it's not ionic. It's giant covalent. So it won't conduct electricity, which is a nightmare. So I can't run electrolysis either. So I have to do the Kroll process. And yes, that is generally, I think it's actually not Kroll, it's Kroll. Kroll process. So we take titanium dioxide and we react it with carbon and chlorine. The carbon is a mop. It's going to mop up the oxygen. So we form TiCl, TiCl4, and CO2. Let's balance the equation. 2 chlorines, and done. So it's quite expensive because you have to use toxic chlorine gas. Once you've made TiCl, you now react TiCl with sodium metal, which is very expensive because we extracted via electrolysis. But I make now salt and titanium. And look how much sodium you need. It's massive. TiCl. Yeah. It's actually TiCl, cool. So that's titanium extraction. It also has to be done under an argon atmosphere. That's a condition. The reason why it has to be done under an argon atmosphere, because if you show it oxygen, anywhere, if oxygen sneaks in from anywhere, it'll hop straight back on with titanium and turn straight back into titanium dioxide. So it's a nightmare. You've got to be careful. It reacts with tickle as well. So you've got to be super careful. So argon atmosphere. There's titanium. Next, we now talk about, here we go, one more. Tungsten. Tungsten, lovely metal, hardest metal in the world, highest melting point in the world. Tungsten is found in a metal, an ore called wolframite, WO3. And we react it with hydrogen gas at 2000 Celsius. And you make W and water. Now, this method is not ideal because hydrogen is explosive. This is not ideal. We need Na to extract. I saw why is titanium expensive? Because you have to use, okay, good question. So the answer for that, why is titanium expensive? Toxic chlorine gas, expensive sodium metal, argon atmosphere. You can also say it's batch, which means you only get to do it once and then you have to restart again. So it's overall crazy expense. Is extracting using electrolysis, and we get also that also from what? That makes no sense. We need sodium. Yes, we need sodium, and when that comes from electrolysis, yes. So not an ideal method for tungsten. The reason being is tungsten also makes another reaction. Why argon not another noble gas? Johan, great question. The air you're breathing. The air. Let's fill a balloon with air. Air is a mixture, and it is a mixture of nitrogen, 78%, oxygen, 21%, argon, 0.8%. It's the most abundant noble gas we have, Johan. There's more argon than anything else. Once everything's gone, once everything is argon, I'll stop. That was terrible. Sorry. It's the most abundant, so we have it. It's the one that we tend to use. Same reason. Yes, exactly the same reason for light bulbs. We fill light bulbs with argon gas. Light bulbs we fill with argon because we have tungsten metal glowing, white hot, producing light at 2400 Celsius. And if we had oxygen there, it would react. We need to get rid of the oxygen, so we fill it with argon. Yes. Okay. That covers. I'm not going to bother with the electrolysis. I've admitted to, okay, that's cool. Other metals, usually other metals with carbon. Why alloys? We covered alloys. Cool. Okay. So what I'm now going to do is I'm just going to quickly run through my preliminary work. Extraction of aluminium, electrolysis. Element, key word there, folks. Element used to make the electrodes is graphite, but the element, of course, is carbon. State whether or not the electrode is positive or negative. Right, this is quite a clever one because we have in here aluminium. Whoa, let's try that again. We've got aluminium 3+ ions and O2- ions. Now, at the bottom of the device, just so you know, is a pipe which is going to let out molten aluminium metal. So we want the aluminium to go to the bottom. That's what this liquid here is. We want liquid aluminium. And we want the oxygen. So at that electrode, if I zoom in even further, the O2- hits the electrode. We go through our half equation, which is 2. This is where I now get to go super fine. 2 O2- goes to oxygen gas and 4 electrons. And I now make oxygen gas. Now, the oxygen gas sadly doesn't leave. It eats the electrode. It starts to eat it away. And we get a second reaction, which produces carbon dioxide. Carbon plus oxygen goes to CO2. So one of the main expenses for aluminium extraction, Mr. Duncan, I have to go have something to do, but thank you so much. I'll watch over it. That's fine. Good job. Thanks, Amira, for letting me know. So we know that aluminium now needs to go to the bottom because we're going to pool it. So we need to make that the negative electrode to attract positives. Opposite to attract. So it's the negative electrode to attract. This is to attract Al3 plus ions. Quite nice to kind of have that detail. Right. Liquid L contains aluminium oxide on one of the person, and the answer is cryolite. We add cryolite because it reduces the melting point of aluminium oxide. Aluminium oxide's original melting point is 2000 Celsius. With cryolite, 1000 Celsius, which is always nice. Reduces the melting point. Next, identify the product at G. So we're going to form the electrodes to form the product formed at G reacts with the electrodes to form carbon monoxide and carbon. Identify this product. The answer is oxygen gas. State why carbon monoxide is poisonous. It does. Mr. Duncan have a second screen to read the chat? Yes, I do, Julian. Yes, indeed. So carbon monoxide is pointed binds to hemoglobin, so it can't carry oxygen. Give a chemical test for carbon dioxide. We've done this in our chemical test webinar, which is so nice to see it happening twice. The test is bubble through lime water, white precipitate formed of calcium carbonate. Nice for me to remind you folks, lime water is calcium hydroxide. There's lime water reacting with CO2 to form calcium carbonate, which is insoluble. What are the two? The strength of solid aluminium depends on the electrostatic force between two of them, cations, Al3+, and the delocalized electrons. Why is aluminium ductile? Ductile is when you can pull it into wires. Valuable is being able to bend it. And they have the same answer, which is lovely. So atoms are in layers, and those layers can slide. In terms of its structure, why is aluminium such a good conductor of electricity? Aluminium, 2 marks. Aluminium has delocalized electrons. These electrons can flow through the structure. Next, state the property that makes aluminium suitable for manufacturing aircraft. It is lightweight or low density for any of you posh physicists. Right, here's the blast furnace. So, raw materials, notice they haven't told us them. So they're going to ask us, iron ore is mixed with 2 other substances. Please name the 2, limestone and coke. Next, write the equation. Oh, love that one. They've pushed us, they've given us iron oxide, and they've given us carbon monoxide. So they're forcing us to do the reduction using carbon monoxide. So you just input these. In goes the carbon monoxide, in goes the iron oxide, and you're going to form CO2, and you're going to form iron metal and balance. Explain which element is reduced in the reaction. Iron element, the element iron is being reduced. The compound is iron oxide, and it's because it's the iron 3+ is gaining 3 electrons, or it is having oxygen removed. Either one is allowed. I actually prefer the oxygen being removed. It's easier. Oh, Bessemer steel process. They've given it in a rather funky container. So write a chemical equation for the reaction between carbon and oxygen to form carbon dioxide. Well, that was easy. Right. Here's our slag formation. So here is our acidic sand, acidic silicon dioxide, and our basic calcium oxide, and we're forming neutral calcium silicate. So the reaction type is neutralization. Next, one problem with using iron is rusting. Name the 2 that you need. Water and oxygen is what you need for rusting. One method is to paint it. State how this prevents it. It coats the surface, preventing oxygen from reaching the iron. It also protects it from water as well. Iron can also be protected from rusting by coating it with zinc. Name this type of protection. Galvanizing. State how this method protects even if the surface of the zinc is scratched. Zinc is more reactive than iron, so the oxygen will react with the zinc before it reacts with the iron. It'll just preferentially choose the zinc over iron because it's way more reactive. So that's pretty easy. It'll just say it's more reactive, so it'll go for him first. You're done. Aluminium is not extracted by heating it with its oxide with carbon monoxide. Why? Aluminium is above carbon in reactivity. Why is iron not extracted by electrolysis? It is way too expensive. Why is silicon dioxide reacted with calcium oxide? SiO2 is acidic, and it will be neutralized by the base calcium oxide. Right, I love this one. There's the picture of sand, giant covalent. This is the picture of SiO2. How did I know that the grey ones are O2? There are more of them. That was it. 2 marks. The grey, so give the particles, the first one, the name is A, there's 1 mark. And there are more greys than blacks. And of course, in silicon dioxide, you can even say there were double. Even though there aren't, you just say there are more. Wondering why silicon dioxide has a high melting point. It's just like diamond. Silicon dioxide is giant covalent in structure. Bonds are covalent bonds only. Covalent bonds are very strong. There are millions of them. Lots of energy needed to break. Blast furnace reappearing again. State the purpose of carbon plus oxygen goes to CO2 is to produce the heat. Carbon plus CO2 goes to carbon monoxide is to produce the reducing agent and produce more heat. That could be a 2-mark question. Produce more heat. But it also what items we need to know. Winkit, there aren't many. Our giants. Let's make that thicker so people can read it. Giant covalents. There aren't covalents. Nice. Giant covalents. We've got silicon. We've got carbon. We've got SiO2. We've got, by the way, that is, of course, diamond and graphite and graphene, but not buckyballs. We've also got TiO2. We have also, what other giants do we have? You're done? That's it? That's all you need? 5? Not many? Next. Go back down. Okay, so calcium, so they ask you to convert words to symbols, which is quite nice. Calcium carbonate, CaCO3, calcium oxide, CaO, carbon dioxide, CO2. And balance, don't forget to balance. Calcium oxide, silicon dioxide, calcium silicate, just add them together. No balancing needed. Explain with reference to the reactions why this is a redox. Right. Oh, not what I want. Sorry. Let's try that again. We're nearly done, folks. We're nearly done, I promise. Of oxygen. Reduction. Red. Gain of oxygen. Ox. You're done. That's it. All you need to say. You can also talk about electrons if you like, but you don't need to. Keep it easy. Talk about oxygen. He's being oxidized, he's being reduced. They're happening at the same time. You're done. Next, order of reactivity. Platinum definitely won't do anything. State the observation made with platinum is added to cold water. No change. Place the 4 metals in order: sodium, magnesium, and platinum. Describe a test to show that there's hydrogen. Collect gas, light with Litzman, squeaky pop sound. Balanced equation, which everybody gets wrong because of him. Watch it, folks. Why do we not put sodium into hydrochloric acid? Because it's way too dangerous. It's probably going to explode. Right. Observations, reactivity. Zinc reacts with copper sulfate. What's going to happen? Right. So if we have zinc metal, I go gray, metal. Well, when that goes into the blue copper sulfate, what is that the zinc metal, that's way too thick, let's try again. The zinc metal is, of course, there's zinc, oh, stop it. Skinny. Come on. Zinc is going to react with the copper sulfate, and it's more reactive. It's going to take it. I'm going to form copper metal and zinc sulfate. So this is blue, and that is colorless. So the first thing that's going to happen is that the blue color is going to fade. It's going to fade to gray. And then we're going to see pink copper metal form on the surface of the zinc rod. we're going to form pink copper metal on the surface. 2 observations. Zinc turns pink because we're forming solid copper. And the blue copper sulfate turns colorless because it's turning from copper sulfate to zinc sulfate. Next, explain why it is not possible to determine the reactivity of copper nickel using these 2 experiments. In a sec, so they have just done zinc plus copper sulfate, and zinc was more reactive. They've then done copper and nickel sulfate, and nothing happened. Right, so zinc is above copper, but copper is less than nickel, but is it less than zinc? We don't know where the zinc comes. Is it above or below zinc? They haven't done the experiment. They haven't performed an experiment between zinc and copper compound. We don't know which is more reactive. That's quite clever. That's hard. That's grade A, that. Maybe even A star. Explain why this is redox. I love how they flickers into electrons. This guy has lost 2 electrons. Lost 2 E minus. And this has gained oxidation. And this is Rig. So nice to talk about it in terms of electrons as well. I think that brings us to the end of the webinar, folks. I want to do one more thing before you guys leave me and abandon me. It was on the web. I just want to show you one more thing. Now, unfortunately, you guys are going to have to just bear with me for this, please. Now, if I go IGCSE, chemistry, I can't remember what paper it was. I was doing it. I was having, physics and maths tutors back up. Paper 2. Let's have a quick look for the metal extraction question on the paper. So, starts off with a bit of multiple choice, goes into covalent bonding, continues with gone into electrolysis. I just want to see if I can find, by the way, nice of me to mention, Faraday's electrolysis calculations are dead, folks. So you can abandon them entirely. I'm just looking for the metal extraction question. There was just a really nice one on a paper that I was looking at with a mirror. I wish I had it on me. And I really don't. That's rather frustrating. So I think what I'm going to do is, if I go back to that Google search, I can't, was it the specimen paper? I can't remember where it was. I think at this point, folks, I'll leave it be at this. I'll find it next time. Okay. Just one more chance to find a question which you might not recognize. I go to my webinars. So these, by the way, I hope this is all the effort I go to. If I go to my season 2 webinars, I can go follow-up work. So each of these booklets I've made, I just want to quickly show you guys a question that you might not have seen. Let's see if I can find one. Hematite, there's the ore names. Oh, there's the blast furnace, of course. I really want it lead. Right. Guys, one more question I want to look at. So, first thing is, my laptop is a pain and doesn't like doing this very much. Right, okay. Importance of reaction, let's go up to this one. G. Gelina is lead sulfide. Still got 10 people here. And Kerusite is lead carbonate, are 2 ores of lead. I haven't talked about lead in this webinar. I need you guys to realize that you have to be able to go beyond what I've done with you. A mining company is considering which of the 2 ores to use for the extraction of lead. If they did this with hematite or magnetite, then they would be choosing magnetite because it has a higher percentage of iron. But in this case, sulfur is a bit more problematic. The equations for the reactions are below. They take lead sulfide, react with oxygen to produce lead oxide. Now that's a problem. Guys, sulfur dioxide, we all in this room know sulfur dioxide is going to be let off to the atmosphere, and it's going to cause acid rain. That's not good. Acid rain. That is not a good gas. Then we do carbon reduction. and then you produce SO2. So then we follow it up with blast furnace as BF. Right, the next option is the process of Carusite is thermal decomposition. So they're going to decompose it and they're going to release carbon dioxide. And they're going to release carbon dioxide again. This is an awful lot of global warming. Pros and cons to both. Both processes form carbon dioxide, which the mining company hopes to sell. Complete the table to show the two uses of carbon dioxide and properties for which each use depends. Right, carbon dioxide, number 1, is used in fire extinguishers. Can anybody think of another use of carbon dioxide? Just before I tell you guys, these are actually really tricky. Give me 2 uses of carbon dioxide gas. Fire extinguisher. Give to plants. Interesting. Do you know what? If you said to bottle it and add to greenhouses, they'd give it to you, Dana. They would, but you'd have to be really clear. But look, the key thing is you need to consider their properties. So what properties are there of carbon dioxide? It is non-toxic and it's odorless and non-flammable. Property, non-flam. So we're going to use it for a extinguisher. Fire extinguisher, exting. Guys, it's put into drinks. It's non-toxic. It's to carbonate drinks. It's to make fizzy drinks. Carbonate drinks. Isn't that crazy? Everyone forgets it. I know, right? Hard though. Next. Right. That's interesting. They've just done all this. Oh, hang on. Hang on. My laptop's being silly. Right. One advantage of losing is that sulfur dioxide produced can cause, one disadvantage is it causes acid rain. Write an equation to show the formation of the acidic solution. I've done this in a previous webinar. SO2 plus H2O goes to H2SO3. Effect. State one effect of acid rain. It will lower pH of soil, killing plants, or it will dissolve statues made of limestone. Many answers. Next, the company uses a sample of Carusite of 500 grams, calculate the maximum mass. We're into a good old calculation. Dry ice. Your hair falls out at what? Can be used for cooling. What are you actually going to put? Because the problem is, you guys have got a very unusual situation here, because in Malaysia, which I have never seen before, it's used for, they put it in boxes with ice cream cakes. Guys, this is not a normal use. It is not something you're going to write down in your exam. Please don't. Anyway, it's nice to see them using a different metal other than, oh, look, thermite, welding train tracks. There we go. Guys, okay, I'm going to end the webinar. It's 8:30. Stop sharing. Right, folks. Thanks so much for coming to the webinar. I really, really appreciate it. I know it's been an hour and a half, but they seem to take around about an hour and 30 minutes for me to run all the way through all the stuff on the specification and to also cover all the questions. It takes about an hour and a half. So thank you for sticking around. I hope you found it useful. It really was a worthwhile thing to do. Please have a look at the follow-up questions. It's worthwhile doing them. 5 questions that I've given you on the preliminary work is never enough to really solidify stuff. Stick with having a look at the follow-up work, and I'll see you all next week. I think my next webinar is going to be on industrial chemistry. Folks, have a lovely evening. I'll see you all tomorrow. Take care, folks.